Look down at your hand. Right now, in this moment, you feel perfectly still. You are sitting in a chair or standing on the floor, seemingly motionless. But that feeling is a profound illusion, because right now, your hand, your chair, your entire body is hurtling through space at a speed that is almost impossible to comprehend. You are on a cosmic ride that never stops, and the most fundamental question about your existence, about the existence of everything you see, is not what it is, but how fast it's spinning. You are spinning with the Earth on its axis at over 1,000 miles per hour. You are spinning around the Sun at 67,000 miles per hour. And you are spinning with the entire Milky Way galaxy at a mind-bending 500,000 miles per hour. Every single thing in the universe, from the smallest subatomic particle to the largest supercluster of galaxies, is caught in this relentless, dizzying, universal dance. But here is the profound mystery. The universe started from a point of almost perfect stillness. The Big Bang was an explosion of energy, yes, but it was a chaotic, featureless expansion. So, where did all this motion come from? Where did the spin, the rotation, the angular momentum that shapes planets, flattens galaxies, and even warps the very fabric of space-time? Where did it all begin? Why is it that when we look out into the cosmos, we see a universe not of static objects, but of colossal, spinning gyroscopes? This is Cosmodepth, and today we are going on a journey to the very edge of physics and philosophy to answer the question that defines our reality. Why does everything in the universe spin? It's a story that starts with a single, almost imperceptible flaw in the universe's beginning, and ends with a force so powerful it can twist light itself. Before we dive into the deep end of the cosmos, take a moment to look at your screen. If you're captivated by these questions, if you feel that pull toward the unknown, then you are already part of the Cosmodepth family. A quick tap on the like button and a subscription helps us keep building this journey, ensuring that the deepest, most compelling stories of the universe keep finding their way to you. It's a small spin of your finger that helps our cosmic channel keep rotating. Now, let's begin the journey. The answer to why everything spins is rooted in one of the most elegant and beautiful principles in all of physics: the conservation of angular momentum. It is the invisible engine that drives the entire cosmic machine. To understand it, forget the galaxies for a moment and picture something simple: an ice skater. When the skater is spinning slowly with their arms outstretched, they are conserving their angular momentum. Now, watch what happens when they pull their arms in close to their body. They instantly begin to spin faster, often dramatically so. They haven't exerted any extra force. They've simply redistributed their mass closer to their axis of rotation. The total amount of angular momentum, a combination of their mass, their velocity, and how far that mass is from the center, must remain the same. If the distance decreases, the velocity must increase. This simple, beautiful principle is not just a trick of the ice rink. It is a cosmic law, and it is the reason why the Earth is a sphere, why Saturn has rings, and why the Milky Way is a flat, spiraling disk. Let's trace this law from the micro to the macro. At the smallest scale, the spin is inherent. Subatomic particles like electrons have an intrinsic property called spin. It's not a physical rotation in the classical sense, but a fundamental quantum number, a form of angular momentum that defines their nature. It is a property of the particle itself, just as mass and charge are. These tiny fundamental spins are the ultimate, irreducible source of all the rotation we see on grand scales. They are the initial, almost philosophical, seed of spin. Now, let's move up to the scale of a star system. Our Sun and its planets were born from a vast, cold cloud of gas and dust, a molecular cloud. This cloud was massive, but it was also huge and diffuse. It was not perfectly still. It had a tiny, almost imperceptible net rotation, a slight, slow swirl caused by the random motions of its constituent particles, or perhaps a slight gravitational tug from a passing star. As gravity began to pull this cloud inward, the cloud started to collapse. The mass, which was once spread out over light years, began to concentrate at the center. And here, the law of conservation of angular momentum kicked in with a vengeance. Just like the ice skater pulling in their arms as the cloud's radius shrank, its rotational speed had to increase dramatically to keep the total angular momentum constant. This increasing spin had a profound effect. It prevented the cloud from collapsing uniformly into a sphere. Instead, the centrifugal force, the outward pulling force created by the rotation, was strongest along the equator of the spin. This outward force resisted the inward pull of gravity in the plane of rotation, but it did nothing to stop the collapse along the axis of rotation. The result? The cloud flattened into a giant spinning disk, the protoplanetary disk. The central mass of this disk became our Sun, and the remaining material in the disk clumped together to form the planets. This process, collapse, acceleration of spin, and flattening into a disk, is the universal recipe for forming stars, planets, and even the rings around gas giants. It is the first great cosmic consequence of angular momentum. The story of spin is not just about local systems, it's about the largest structures in the universe, galaxies. And the origin of their rotation is a far more complex and fascinating tale, one that takes us back to the very first moments after the Big Bang. The early universe, about 380,000 years after the Big Bang, was a smooth, hot soup of plasma, as evidenced by the cosmic microwave background, CMB radiation. The CMB is a snapshot of this time, and it shows the universe was almost perfectly uniform. The temperature variations, the tiny lumps and ripples that would eventually grow into galaxies, were only 1 part in 100,000. It was a universe with almost no structure, and critically, almost no net rotation on the scale of a proto-galaxy. So, how did these smooth, non-spinning lumps of matter acquire the colossal angular momentum needed to create a galaxy like the Milky Way, which spins so fast it takes 250 million years for the Sun to complete one orbit? The answer lies in a process called tidal torque. Imagine 2 of those tiny, slightly denser lumps of matter, the proto-galaxies, floating near each other in the early universe. While they are gravitationally attracting each other, they are not pulling directly center to center. Because the distribution of matter in the early universe was not perfectly uniform, the gravitational pull from one lump on the other is slightly off-center. This off-center pull creates a torque, a twisting force, much like pushing on a door handle away from the hinges. This torque doesn't pull the proto-galaxies together in a straight line. It makes them twist around each other. This twisting motion is what transfers a small, initial, random angular momentum from the large-scale structure of the universe into the smaller, collapsing proto-galactic cloud. The crucial part of this process involves dark matter halos. Galaxies do not spin alone. They are embedded within massive invisible spheres of dark matter. The dark matter halo acts as the gravitational scaffolding for the visible galaxy. The angular momentum of the visible galaxy is, in fact, only a small fraction of the total angular momentum of the entire system. The tidal torques we discussed primarily act on the dark matter halo, transferring angular momentum from the surrounding large-scale structure. The dark matter then transfers this spin to the baryonic ordinary matter through gravitational interactions. This is a crucial, often overlooked, step in the cosmic dance. The efficiency of this angular momentum transfer from the dark matter halo to the visible disk is a key area of research. If the transfer is too efficient, the galaxy spins too fast and tears itself apart. If it is too slow, the galaxy remains a fluffy, non-spinning blob. The delicate balance that results in a beautiful spiral galaxy is a testament to the finely tuned physics of dark matter and its gravitational influence. As these clouds collapse under their own gravity, the tidal torque process continues, and the conservation of angular momentum takes over again. A cloud that was once light years across, spinning at a glacial pace, shrinks by a factor of 100,000. To conserve its angular momentum, its rotational velocity increases by the same factor. This is how the slow, gentle twist of the early universe is amplified into the dizzying, 500,000 mile-per-hour spin of a mature spiral galaxy. This process explains a key feature of the cosmos, the Hubble sequence of galaxies. Spiral galaxies, like the Milky Way, are the classic spinning disks. They acquired a high amount of angular momentum early on, which forced them to flatten out. Their rotation is the dominant force shaping them. The spiral arms themselves are a result of differential rotation, where the inner parts of the galaxy rotate faster than the outer parts, creating a density wave that maintains the spiral pattern over billions of years. Elliptical galaxies are massive, often football-shaped, and contain very little net rotation. They are thought to have formed either from clouds with very little initial angular momentum, or, more commonly, from the merger of two or more spiral galaxies. When two spinning disks collide, their angular momentum vectors often cancel each other out, resulting in a large, non-spinning, spheroidal, elliptical galaxy. The spin of a galaxy is therefore a fossilized memory of the gravitational interactions it experienced billions of years ago. It is a record of the cosmic dance of the early universe, imprinted on the stars and gas we see today. The study of this angular momentum distribution across different galaxy types is one of the most fundamental areas of modern astrophysics, providing crucial constraints on models of galaxy formation and evolution. The total angular momentum is a conserved quantity, but its distribution and transfer are the keys to understanding the entire cosmic architecture. If conservation of angular momentum shapes stars and galaxies, what happens when you take that spin and compress it to the absolute limit of physics? You get the most extreme spinners in the universe. Black holes. Not all black holes spin, but the vast majority are thought to. These are known as Kerr black holes, named after the physicist Roy Kerr, who first described them mathematically in 1963. The Kerr metric is the solution to Einstein's field equations that describes the space-time geometry around a rotating, uncharged mass. And their spin is not just a curiosity. It is a fundamental property that fundamentally changes the nature of space-time around them, leading to some of the most bizarre and powerful phenomena in the cosmos. A non-spinning black hole, a Schwarzschild black hole, is defined simply by its event horizon, the point of no return. But a spinning black hole adds a second, critical boundary: the ergosphere. The ergosphere is a region of space-time outside the event horizon where the rotation of the black hole is so intense that it drags space-time itself around with it. This is the phenomenon known as frame dragging, or the Lenz-Thirring effect. Imagine space-time as a thick, viscous fluid. A spinning black hole is like a giant, rapidly rotating ball submerged in this fluid. The ball's rotation twists the fluid around it. In the ergosphere, this twisting is so powerful that it becomes impossible to remain stationary. No matter how much thrust you apply, you must rotate with the black hole. You are literally forced to move by the warped geometry of the universe. The ergosphere is a region of positive energy density, but it is also a place where the rotational energy of the black hole can be tapped. This frame dragging has profound consequences. It is the engine behind the most powerful phenomena in the cosmos: quasars. Matter falling into a spinning black hole forms an accretion disk, a swirling vortex of superheated gas and plasma. As this matter spirals inward, the frame dragging effect organizes the magnetic fields around the black hole. This organization, combined with the immense rotational energy, allows the black hole to launch two incredibly powerful, tightly focused jets of plasma, the quasar jets, outward along its axis of rotation. These jets can extend for millions of light years, outshining entire galaxies. The mechanism for this energy extraction is theorized to be the Blandford-Snarjek process, which uses the magnetic field lines anchored in the spinning black hole's ergosphere to channel the rotational energy into the jets. But there is an even more direct, almost science fiction-like way to extract energy from a spinning black hole, theorized by Sir Roger Penrose in 1969. The Penrose process. The Penrose process is a theoretical mechanism that shows how the rotational energy of a spinning black hole can be converted into usable energy. It works like this. A particle enters the ergosphere and splits into two fragments. One fragment, with negative energy relative to a distant observer, falls into the black hole. The other fragment, with more energy than the original particle, escapes the black hole. By sacrificing a particle with negative energy, the black hole's rotational energy is reduced, and the escaping particle carries away the excess energy. This process demonstrates that the spin of a black hole is not just a property, but a vast reservoir of kinetic energy, a cosmic battery storing the angular momentum of everything that has ever fallen into it. The Penrose process demonstrates efficiencies ranging from 5% to 35%, with peak efficiency achieved at high spin, but diminishing with increased charge or other factors. In essence, the spin of the black hole is a cosmic dynamo, converting rotational energy into the most luminous and energetic structures we know. The black hole is not just a gravitational sink. It is a machine that recycles the angular momentum of infalling matter into raw, staggering power. The very existence of these spinning behemoths and the extreme physics they exhibit is a powerful testament to the conservation of angular momentum taken to its absolute mind-bending limit. The study of these Kerr black holes is not just a niche area of astrophysics. It is the ultimate laboratory for testing the boundaries of general relativity itself. Let us now descend from the cosmic scale of black holes and galaxies to the subatomic world, where the concept of spin takes on an entirely new and even more fundamental meaning: quantum spin. At the smallest scale, the spin is inherent. Subatomic particles like electrons, protons, and neutrons all possess an intrinsic property called spin. It's crucial to understand that this is not a physical rotation in the classical sense. The electron is considered a point particle, and if it were physically spinning to produce its observed angular momentum, its surface would have to be moving faster than the speed of light, which is impossible. Instead, quantum spin is a fundamental quantum number, a form of angular momentum that defines their nature. It is a property of the particle itself, just as mass and charge are. These tiny fundamental spins are the ultimate, irreducible source of all the rotation we see on grand scales. They are the initial, almost philosophical, seed of spin. The most profound consequence of quantum spin is encapsulated in the spin statistics theorem. This theorem, a cornerstone of quantum field theory, dictates the fundamental behavior of all particles in the universe based solely on their spin value. It states that fermions, particles with half-integer spin, like 1 by 2, 3 by 2, 5 by 2, such as electrons, quarks, and neutrinos, obey the Pauli exclusion principle. This means no two identical fermions can occupy the same quantum state simultaneously. This principle is the reason atoms have structure, why elements are stable, and ultimately, why matter does not collapse into a single point. The spin of the electron, in particular, is what forces electrons into different energy shells around the nucleus, giving rise to the periodic table, chemistry, and all the complexity of the material world. Bosons, particles with integer spin, like 0, 1, 2, such as photons, gluons, and the Higgs boson, do not obey the Pauli exclusion principle. They can all occupy the same quantum state, which is why they are the force carriers of nature. Photons, the carriers of the electromagnetic force, are bosons with a spin of 1. The spin statistics theorem is a deep connection between the intrinsic angular momentum of a particle and its statistical behavior. It is a fundamental law that links the geometry of space-time through angular momentum to the very nature of matter. Without quantum spin, the universe would be a featureless, chaotic soup. It is the spin that provides the necessary order and structure for the existence of atoms, molecules, and ultimately, life. Furthermore, quantum spin plays a critical role in the symmetry-breaking events of the early universe. In the moments after the Big Bang, the universe was a place of high symmetry, where forces were unified. As the universe cooled, these symmetries were spontaneously broken, giving rise to the distinct forces and particles we see today. The slight preference for one spin direction over another in certain particle interactions, known as parity violation, is a key piece of evidence for this symmetry breaking. This tiny asymmetry, perhaps a microscopic bias in how particles decayed, gave matter the slightest advantage over antimatter, leaving behind the atoms that form stars, galaxies, and eventually us. Spin may be the fingerprint of that ancient choice, a subtle preference written into the laws of physics that tipped the scales toward existence. The universal spin, therefore, is not confined to the macroscopic world of planets and galaxies. It is a property of existence itself, a fundamental quantum property that dictates the very structure and stability of matter. It is the spin of the electron that prevents your hand from passing through the table, and it is the spin of the photon that allows light to carry information across the cosmos. The spin is the enduring link between the first moments of creation and the present moment of observation. We have traveled from the quantum realm to the black hole, but our journey into the universal spin is not complete until we reach the largest scale of all, the cosmic web. Galaxies are not scattered randomly. They are organized into a vast filamentary structure known as the cosmic web, with clusters of galaxies connected by long strands of gas and dark matter, separated by immense voids. Recent observations and simulations have revealed a stunning and unexpected fact. Even the filaments of the cosmic web are spinning. These colossal structures, spanning hundreds of millions of light years, are rotating around their long axes. This is the largest scale of rotation ever observed, and it is a direct consequence of the tidal torques acting on the initial density fluctuations in the early universe. The spin is not just confined to individual galaxies. It is a property of the entire large-scale structure of the cosmos. This discovery confirms the universal nature of angular momentum and its role as the primary sculptor of the universe's architecture. The rotation of these filaments is a direct, observable consequence of the initial conditions set during the Big Bang, amplified by the gravitational influence of dark matter over billions of years. It is the ultimate expression of the conservation of angular momentum on a cosmological scale. The concept of spin is also central to the ongoing quest for a theory of quantum gravity. At the subatomic level, the spin of a particle is a fundamental property, a quantum number. At the cosmic level, the spin of a black hole is a property of space-time itself, described by general relativity. Bridging this gap is the ultimate challenge in modern physics. Theories like loop quantum gravity and string theory attempt to unify these two descriptions. In loop quantum gravity, space-time itself is quantized, made up of discrete loops, and the spin of these loops is a fundamental component of the theory. The theory suggests that the fabric of space-time itself is woven from these tiny spinning quanta. In string theory, all particles are tiny, vibrating strings, and the different modes of vibration and rotation of these strings give rise to the different particle properties, including spin. The universal spin, therefore, is not just a cosmological curiosity. It is a theoretical battlefield where the deepest secrets of the universe are being fought over. The ultimate answer to why does everything spin may well be the answer to how does the universe work at its most fundamental level. The spin is the enduring link between the quantum world and the cosmos, the single thread that runs through all scales of existence. We must also consider the fate of spin in the far future. If everything is spinning, what is the ultimate fate of all this angular momentum? Will the universe spin forever, or will the great cosmic dance eventually slow to a halt? Our own planet is a perfect example of a spinning object that is slowly, inexorably slowing down due to tidal friction caused by the moon. The angular momentum lost by the Earth's spin is not destroyed. It is transferred to the moon's orbit, causing the moon to slowly spiral outward. The spin of galaxies will also eventually fade, but through a different mechanism: mergers and accretion. As galaxies age, they continue to interact and merge, When two spiral galaxies merge, their angular momentum vectors often cancel each other out, resulting in a large, non-spinning elliptical galaxy. Over trillions of years, as the universe expands and the cosmic web continues to evolve, the largest structures will continue to merge. The elegant, spinning spirals will be replaced by massive, non-spinning spheroids. The energy of the spin will be radiated away in the form of gravitational waves and dispersed as heat. The universal spin, which began with a tiny necessary flaw in the Big Bang, will end with the final, slow, and inexorable triumph of entropy. The cosmic dance will slow, the music will fade, and the universe will finally approach the state of perfect stillness and maximum disorder. But that is a story for a time far beyond our comprehension. For now, we live in the age of spin, a vibrant, dynamic, and beautiful cosmos where motion is life, and the great dance is in full swing. The universal spin is not merely a mechanical process. It is a fundamental pillar of our reality, inextricably linked to the concepts of time and life itself. Imagine the universe without motion, no planets orbiting, no stars turning, no atoms vibrating, only stillness. In that frozen reality, there would be no events, no change, and therefore no time. Time, at its most fundamental level, isn't something the universe has. It's something the universe does. It's the measure of change, the rhythm of motion unfolding from one moment to the next. And spin, more than anything else, keeps that rhythm alive. Every rotation in the cosmos, a planet turning, a pulsar flashing, an electron spinning, is a way of marking time. A single spin equals a single tick in the universe's clockwork. Without these cycles, there would be no reference for before or after. Spin gives structure to time itself. The arrow of time we experience exists because energy is always moving from organized to disordered states. Entropy. Spin is one of the key ways that process unfolds, as rotational energy is constantly being dissipated through friction, radiation, and collisions, driving the universe forward in time. The universal spin is a fundamental filter in the search for life beyond Earth, a key component of the anthropic principle. The fact that the universe is not perfectly still, that it has a non-zero, local angular momentum, is a necessary condition for our existence. Without the spin, there would be no centrifugal force to flatten the molecular clouds into protoplanetary disks, and without disks, there would be no planets. Furthermore, a planet's rotation is necessary to generate a protective magnetic field, the geodynamo. This field shields us from deadly solar radiation. Any potentially habitable exoplanet must be spinning at a rate sufficient to maintain this shield. Mars, which spins more slowly and lost its magnetic field, is a stark reminder of this cosmic prerequisite. The rotation of the Milky Way itself is crucial. Our solar system is positioned in the galactic habitable zone, a ring far enough from the chaotic, radiation-filled center of the galaxy, but close enough to have access to the heavy elements forged in previous generations of stars. Our stable, near-circular orbit around the galactic center is a consequence of the galaxy's organized spin. If our orbit were highly elliptical, we would pass too close to the dangerous inner regions, sterilizing the planet. The universal spin is the cosmic gatekeeper. It sets the rules of the game, dictating where and how life can emerge and survive. The rotation of the cosmos is the ultimate reminder that the universe is a finely tuned, dynamic symphony where motion is life and the dance never ends. torsion and quantum gravity. Finally, the deepest connection between spin and the fabric of reality lies in the concept of torsion. In some extensions of general relativity, such as the Einstein-Cartan theory, space-time is not only curved by mass and energy, gravity, but also twisted by the intrinsic spin of matter, torsion. This theory suggests that the quantum spin of all the fermions in the universe, the electrons, quarks, and neutrinos, collectively creates a subtle, universal twisting of space-time. This is a profound idea. The microscopic spin of every particle in your body and in the stars is not just a quantum number, but an active participant in shaping the geometry of the entire cosmos. If this theory is correct, the answer to why does everything spin is that the spin itself is a fundamental geometrical property of the universe, as essential as mass and energy. The ultimate mastery of spin may be the key to the stars, as some speculative theories suggest that a controlled, localized torsion could be a key ingredient in manipulating the vacuum energy required for a warp drive. Let us rewind the cosmic clock, not just to the formation of the first stars, but to the very beginning, the Big Bang and the subsequent inflationary epoch. This is where the story of spin truly begins, in a universe that was, paradoxically, almost perfectly still. The standard cosmological model, the lambda CDM model, posits that the universe began in a state of near-perfect homogeneity and isotropy. The cosmic microwave background, CMB, the oldest light in the universe, is the ultimate proof of this. It is a thermal bath of radiation, a relic of the universe when it was only 380,000 years old, and it shows the universe was uniform to an astonishing degree. The temperature variations, the seeds of all the future structure, were only 1 part in 100,000. It's like looking at the surface of a perfectly smooth pond with only the tiniest, almost imperceptible ripples. So, how do you get colossal, rapidly spinning galaxies from a state of near-perfect uniformity? The answer lies in those tiny ripples and the turbulent physics of the very early universe. The prevailing theory for the origin of these initial ripples is cosmic inflation. In the first tiny fraction of a second after the Big Bang, the universe expanded exponentially, stretching a microscopic region of space to astronomical size. This rapid expansion smoothed out any pre-existing curvature or irregularities, making the universe flat and uniform. However, quantum mechanics dictates that nothing is ever truly still, even in the vacuum of space. During inflation, the vacuum was a seething cauldron of quantum fluctuations. These are fleeting, random energy variations that constantly pop in and out of existence. The incredible speed of inflation stretched these microscopic quantum fluctuations into macroscopic density variations. These are the ripples we see in the CMB. But here is the critical point for our story. These fluctuations were not just density variations. They also contained a tiny, net amount of vorticity, or rotational motion. Imagine a turbulent river. Even if the river as a whole is flowing straight, there are tiny, random eddies and swirls everywhere. The quantum vacuum was a similar soup of random microscopic twists. Inflation magnified these random twists, preserving them as the initial angular momentum of the protogalactic clouds. The evidence for this primordial twist is not just theoretical. It's being sought in the polarization of the CMB. Light waves, as we discussed, have a property called polarization, which is related to their spin. When the light of the CMB interacted with the early plasma, it became polarized. The polarization patterns can be broken down into two types: E modes and B modes. E modes are curl-free patterns, like swirls that all point inward or outward. They are caused by density variations. B modes. These are patterns with a curl, a distinct swirling or twisting signature. Primordial gravitational waves are ripples in spacetime generated during the inflationary epoch. These waves literally twisted the fabric of spacetime itself as they propagated through the early universe. This twisting motion would have imprinted a B-mode polarization signature onto the CMB light. Finding these B-modes is the holy grail of cosmology because it would be a direct, observable confirmation of inflation and, crucially, a measurement of the primordial rotational energy of the universe. It would be the universe's birth certificate, signed with a twist. Current and future CMB experiments, such as the Simons Observatory and CMBS-4, are meticulously mapping this polarization to unlock the secrets of this initial spin. The data from these observatories will either confirm the Standard Model's prediction of a nearly twist-free universe, or reveal a global, cosmic rotation that would fundamentally rewrite the laws of physics. The fact that we are looking for a twist in the oldest light in the universe underscores how fundamental rotation is to the cosmic story. The initial angular momentum of a proto-galaxy is incredibly small. It is not enough to explain the rapid spin of a galaxy today. The seed of rotation, the initial twist, had to be amplified. This amplification is the job of gravity, working through the mechanism of tidal torques. The initial fluctuations in the early universe were not perfectly spherical. They had slight, irregular shapes, which can be mathematically described by their quadrupole moment. A quadrupole moment is a measure of how much a mass distribution deviates from a perfect sphere. Imagine an object that is slightly elongated, like a football, rather than a perfect basketball. When two of these slightly non-spherical proto-galactic clouds are close to each other, the gravitational pull between them is not perfectly aligned with their centers. The gravitational force acts more strongly on the closer, elongated parts of the clouds than the farther parts. This difference in force creates a lever arm, which generates a torque, a twisting force. This torque is what transfers angular momentum from the large-scale, chaotic motions of the surrounding universe into the collapsing proto-galaxy. The tidal torque process is a slow, patient dance of gravity. It continues for billions of years as the proto-galaxy collapses and interacts with its neighbors. The total angular momentum of the system is conserved, but it is constantly being transferred from the orbital motion of the proto-galaxies around each other into the spin of the individual proto-galaxies. This process is highly dependent on the surrounding environment. A proto-galaxy in a dense cluster, surrounded by many neighbors, experiences stronger and more frequent tidal torques, leading to a higher final spin. Conversely, a proto-galaxy in a quiet void experiences weaker torques and ends up with less spin. This explains the observed correlation between a galaxy's environment and its rotational properties. The key takeaway is that the spin of a galaxy is a two-stage process. It starts with a tiny random quantum twist inherited from the Big Bang, and is then amplified over billions of years by the gravitational twisting of its neighbors. It is a beautiful demonstration of how the conservation of angular momentum acts as a cosmic memory, preserving and magnifying the initial, almost imperceptible flaws of the universe's birth. The tidal torque mechanism is further complicated and dominated by dark matter. As we established, galaxies are embedded in massive, invisible dark matter halos. These halos are the primary recipients of the tidal torques. The dark matter halo is the gravitational scaffolding. It is the dark matter that first absorbs the angular momentum from the cosmic web. The baryonic matter, the gas and dust that will eventually form stars, is initially mixed with the dark matter. As the system collapses, the gas is able to cool and fall to the center of the halo, while the dark matter remains more diffuse. During this collapse, the dark matter halo acts as a massive, invisible flywheel. It transfers its acquired angular momentum to the gas. The gas, being able to cool and radiate energy, collapses much more efficiently. To conserve the angular momentum it inherited from the dark matter, the gas must spin up dramatically as its radius shrinks. This is the final crucial step that transforms a slightly twisted lump of dark matter into a rapidly spinning, flat disk of stars, a spiral galaxy. The efficiency of this transfer is a major puzzle in galaxy formation. If the gas perfectly conserved its angular momentum, the resulting galaxies would be far too large and diffuse compared to what we observe. This suggests that some of the angular momentum is lost or redistributed during the collapse, perhaps through feedback from supernovae or active galactic nuclei. This is the angular momentum catastrophe problem, a long-standing challenge in cosmology that shows the simplicity of the conservation law is often masked by the complexity of the cosmic environment. The spin of a galaxy is a delicate, hard-won prize, a balance struck between the initial quantum turbulence of the Big Bang, the long-range gravitational twisting of the cosmic web, and the invisible scaffolding of dark matter. It is a story of motion being conserved, transformed, and ultimately made visible in the breathtaking spiral arms we see across the night sky. We must now return to the ultimate expression of spin in the cosmos, the black hole. The brief mention earlier only scratched the surface of the mind-bending physics that occurs when angular momentum is compressed to its absolute limit. This is where the universe's spin doesn't just shape matter, it shapes space-time itself. When Carl Schwarzschild first solved Einstein's field equations for a non-rotating, spherically symmetric mass, he gave us the Schwarzschild black hole, defined by a single event horizon. But the universe is not static. Almost every object in the cosmos rotates, and when a massive star collapses, it carries its angular momentum with it. In 1963, Roy Kerr provided the solution for a rotating black hole, the Kerr metric, which is one of the most important exact solutions in general relativity. The Kerr metric reveals that a spinning black hole is defined by two boundaries, not one: the event horizon and the static limit. The event horizon is still the point of no return. However, unlike the Schwarzschild horizon, the Kerr horizon is ablate, flattened at the poles due to the centrifugal force of the spin. The faster the black hole spins, the more flattened it becomes. The static limit, or ergosphere, is the outer boundary, and it is the region where the frame dragging effect begins. The most profound consequence of the Kerr metric is frame dragging, or the lens-thirring effect. This is not a metaphor. It is a literal twisting of the fabric of space-time caused by the black hole's rotation. Imagine space-time as a massive, swirling vortex. The black hole is the drain at the center, and its spin is like a giant paddle wheel. Any object, even a beam of light, that enters the ergosphere is forced to rotate with the black hole. Inside this region, there is no such thing as a stationary observer. You must move. If you tried to hold a flashlight steady, the light beam would be dragged around the black hole, proving that the very coordinates of space and time are being twisted. The ergosphere is shaped like a flattened ellipsoid that touches the event horizon at the poles and bulges out significantly at the equator. The size of the ergosphere is directly proportional to the black hole's spin. A maximally spinning black hole, one spinning at the theoretical limit, where the event horizon almost touches the singularity, has the largest ergosphere, maximizing the frame dragging effect. The ergosphere is not just a bizarre region of twisted spacetime. It is a vast, untapped energy reservoir. The rotational energy of a spinning black hole is immense. Up to 29% of its total mass energy can be stored in its spin. The Penrose process provides a theoretical mechanism to extract this energy. It relies on the fact that within the ergosphere, particles can momentarily have negative energy relative to a distant observer. The process works as follows. A particle, let's call it particle A, enters the ergosphere. Particle A decays into two fragments, particle B and particle C. Particle B, the fragment with negative energy, falls into the black hole. Particle C, the escaping fragment, carries away more energy than the original particle A had, effectively extracting the rotational energy from the black hole. This mechanism is a direct consequence of the frame dragging effect. By allowing a particle to fall in with negative energy, the black hole's total mass energy is reduced, and since the mass is proportional to the square of the spin, the black hole slows down. The Penrose process demonstrates that the spin of a black hole is a cosmic battery, a storehouse of kinetic energy that can be tapped by advanced civilizations. The maximum theoretical efficiency of the Penrose process is nearly 20%, a staggering figure for an energy source. While the Penrose process is theoretical, the Blandford-Znajek mechanism is the leading candidate for explaining the most powerful observed phenomena in the universe. The jets of quasars and active galactic nuclei, A, G, N. This mechanism is a more realistic, electromagnetic way to tap the black hole's spin. It proposes that magnetic field lines originating from the accretion disk are dragged and twisted by the spinning black hole. This twisting creates a powerful electric field that channels the black hole's rotational energy into two tightly collimated jets of plasma, shooting out at near the speed of light. The black hole acts like a giant spinning dynamo, converting rotational energy into electromagnetic power. The power output of these jets is directly proportional to the square of the black hole's spin and the strength of the magnetic field. A fast-spinning black hole is a powerful quasar. A slow-spinning one is a quiet one. The spin of the black hole, therefore, is the ultimate cosmic engine. It is the force that warps spacetime, creates the ergosphere, and powers the most luminous objects in the universe. It is the final, dramatic chapter in the story of angular momentum, where motion is not just conserved, but actively weaponized by the laws of physics. The study of these extreme spinners is the most direct way we have of probing the limits of general relativity and the fundamental nature of gravity. It's one thing to theorize about spin, but how do we actually know that everything is spinning? The evidence for the universal spin is one of the most compelling narratives in the history of science, a story told through a series of increasingly sophisticated observations that span from a simple pendulum to the ripples in space-time itself. The first definitive, observable proof of Earth's rotation came not from the stars, but from a simple experiment conducted in 1851 by the French physicist Léon Foucault. Before Foucault, the Earth's rotation was a hypothesis, a theory supported by astronomical observations. Foucault made it a physical reality. He suspended a 67-meter-long pendulum with a 28-kilogram brass bob from the dome of the Pantheon in Paris. He set it swinging back and forth in a straight line. To the amazement of the crowds, the plane of the pendulum's swing appeared to slowly rotate clockwise over the course of the day. The pendulum was not changing its direction of swing. Due to the principle of inertia, its plane of oscillation remained fixed in space. It was the Earth rotating beneath it that caused the apparent shift. At the North Pole, the pendulum would complete a full 360-degree rotation in exactly 24 hours. At the equator, it would not rotate at all. The rotation observed in Paris was the precise angle predicted by the Earth's latitude. Foucault's pendulum was the first direct physical demonstration that we live on a spinning world, a testament to the power of inertia and angular momentum. For distant stars and galaxies, we cannot use a pendulum. Instead, we rely on the subtle shift in the light they emit, a phenomenon known as the Doppler effect. When an object is moving toward an observer, the light waves it emits are compressed, shifting the light toward the blue end of the spectrum, blue shift. When an object is moving away, the light waves are stretched, shifting the light toward the red end of the spectrum, redshift. When we observe a star, we are not looking at a single point of light, but a rotating sphere. The side of the star rotating toward us is blue shifted, and the side rotating away from us is red shifted. This difference in the Doppler shift across the star's surface causes the spectral lines in the star's light to broaden. The wider the spectral line, the faster the star is spinning. This technique, called stellar spectroscopy, allows astronomers to measure the rotational velocity of stars billions of miles away, confirming that rotation is a universal characteristic of stars. The most spectacular evidence of stellar spin comes from pulsars, a type of rapidly spinning neutron star. A neutron star is the collapsed core of a massive star, a sphere only about 20 kilometers wide, yet containing more mass than our Sun. As the star collapses, the conservation of angular momentum causes its rotation to speed up dramatically, like an ice skater pulling in their arms. This results in neutron stars spinning hundreds of times per second. Their powerful magnetic fields are misaligned with their rotation axis, causing them to emit beams of radio waves from their magnetic poles. As the star spins, these beams sweep across Earth, creating a precise rhythmic pulse, much like a cosmic lighthouse. Pulsars are the most accurate natural clocks in the universe. Their rotation is so stable that scientists use them to measure time itself. The regularity of their spin is a direct, observable consequence of the conservation of angular momentum taken to its extreme. The most recent and profound evidence for cosmic spin comes from the detection of gravitational waves by observatories like LIGO and Virgo. When two massive spinning objects, such as two black holes or two neutron stars, spiral into each other and merge, they create cataclysmic ripples in the fabric of spacetime. These ripples carry away energy and, crucially, angular momentum. The gravitational wave signal, the chirp that LIGO detects, is not a simple tone. It is a complex waveform that contains the signature of the object's masses and their spins. By analyzing the final moments of the merger, scientists can determine how fast the black holes were spinning before they collided. The very existence of these spinning black holes and the energy they radiate as they merge is the ultimate physical proof of the conservation and transfer of angular momentum in the most violent events in the cosmos. Furthermore, the Gravity Probe B mission, launched by NASA, provided the first direct high-precision measurement of frame dragging around the Earth. By using 4 ultra-precise gyroscopes, the mission confirmed that the Earth's rotation slightly twists the space-time around it, exactly as predicted by the Kerr metric and general relativity. This confirmed that the universal spin is not just about the movement of matter in space, but the movement of space itself. From Foucault's pendulum to the echoes of merging black holes, the evidence is overwhelming and consistent. The universe is a place of relentless, fundamental motion, and the conservation of angular momentum is the law that governs it all. The universal spin is not an isolated phenomenon. It is the fundamental engine that drives one of the most powerful and life-sustaining forces in the cosmos: magnetism. The connection between motion and magnetism is a deep, inseparable relationship, governed by the laws of electromagnetism, and it is the spin that converts mechanical energy into the invisible shields that protect life. The most immediate and vital example of this connection is the geodynamo, the mechanism that generates Earth's magnetic field. This field is not a permanent magnet. It is a dynamic, constantly changing field generated by the motion of molten metal deep within our planet. The Earth's core is composed of a solid inner core and a liquid outer core, primarily made of iron and nickel. The Earth's rotation, combined with the convection currents driven by the cooling of the core, causes this electrically conductive fluid to move in complex swirling patterns. This motion of a conductor within a magnetic field generates an electric current, which in turn generates a new, stronger magnetic field. This is a self-sustaining feedback loop, a massive, planetary-scale dynamo powered by the Earth's spin and internal heat. The resulting magnetic field extends thousands of miles into space, forming the magnetosphere. This magnetosphere acts as a gigantic, invisible shield, deflecting the constant stream of charged particles known as the solar wind, which is ejected from the Sun. Without this shield, the solar wind would strip away our atmosphere over time, and the surface of the Earth would be constantly bombarded by lethal radiation. The spin of the Earth is therefore the ultimate guardian of life, a cosmic prerequisite for habitability. The Sun, too, is a massive dynamo, and its magnetic field is far more complex and violent than Earth's. The Sun does not rotate as a solid body. Its equator spins faster than its poles, a phenomenon called differential rotation. This differential rotation, combined with the convection of the Sun's plasma, twists and stretches the Sun's internal magnetic field lines. Over an 11-year cycle, the magnetic field becomes increasingly tangled, eventually erupting through the surface in the form of sunspots, solar flares, and coronal mass ejections, CMES. These violent events are a direct consequence of the Sun's turbulent, differential spin. The magnetic field lines get so twisted that they snap, releasing immense amounts of energy. The Sun's magnetic field is a chaotic, dramatic expression of the conversion of rotational energy into magnetic energy. Even on the scale of galaxies, spin drives magnetism. The Milky Way is permeated by a weak, large-scale magnetic field. This field is thought to be generated by the galactic dynamo, a process similar to the geodynamo, but on a colossal scale. The differential rotation of the galaxy, where stars and gas closer to the center rotate faster than those farther out, twists the seed magnetic fields present in the interstellar medium. This twisting, combined with the turbulent motion of gas clouds, amplifies the magnetic field over billions of years. This galactic magnetic field plays a crucial role in star formation, channeling gas clouds and influencing the propagation of cosmic rays. The universal spin, from the quantum spin of an electron that creates local magnetism, to the rotation of a planet that creates a protective magnetosphere, to the differential rotation of a galaxy that creates a cosmic magnetic web, is the invisible hand of electromagnetism. It is the force that converts the simple act of motion into the complex, life-sustaining, and violent magnetic phenomena that permeate the entire cosmos. The spin is the engine, and magnetism is its most visible and vital product. We have explored the origin and the present state of the universal spin, but what about its final chapter? If motion is life, what happens when the great cosmic dance finally begins to slow? The ultimate fate of the universal spin is a story written in the slow, relentless work of tidal forces and the final, inexorable triumph of entropy. Our own Earth-Moon system provides a perfect, observable example of the gradual dissipation of spin. The Earth's rotation is decelerating due to tidal friction caused by the Moon. The Moon's gravity pulls on the Earth's oceans, creating bulges of water on both the near and far sides. The Earth's rotation attempts to drag these bulges ahead of the Moon-Earth line. This dragging creates friction, which acts as a brake on the Earth's spin. The result is that the Earth's day is getting longer by about 2.3 milliseconds per century. This is a tiny, almost imperceptible change, but over geological timescales, the effect is profound. 400 million years ago, an Earth day was only 22 hours long. The angular momentum lost by the Earth's spin is not destroyed. It is transferred to the Moon's orbit, causing the Moon to slowly spiral outward, moving about 3.8 centimeters away from Earth each year. This process will continue until the Earth's rotation period matches the Moon's orbital period, a state called tidal locking. At that point, the Earth will always show the same face to the Moon, and the great brake will be released. The spin will not have stopped, but it will have been synchronized and stabilized. For the Earth and Moon, this final state is still billions of years away, but it is an inevitable, physical consequence of the conservation of angular momentum and the relentless work of tidal forces. The spin of galaxies will also eventually fade, but through a different, more dramatic mechanism: mergers and accretion. As galaxies age, they continue to interact and merge. As we discussed, when two spiral galaxies merge, their angular momentum vectors often cancel each other out, resulting in a large, non-spinning elliptical galaxy. Our own Milky Way is on a collision course with the Andromeda Galaxy. In about 4.5 billion years, they will merge to form a new, giant elliptical galaxy nicknamed Milkomeda. This merger is not a head-on collision of stars, but a slow, gravitational dance. The two spinning disks will pass through each other multiple times, their gravitational fields tugging and tearing at each other. The vast, organized angular momentum of the two spirals will be converted into the random, chaotic orbital energy of the stars in the resulting elliptical galaxy. The elegant dynamic rotation will be replaced by a massive spheroidal structure with little net rotation. Over trillions of years, as the universe expands and the cosmic web continues to evolve, the largest structures will continue to merge. The elegant spinning spirals will be replaced by massive non-spinning spheroids. The energy of the spin will be radiated away in the form of gravitational waves and dispersed as heat. The spin, the great organizing force of the universe, will eventually be a victim of its own success. The structures it created will collide and merge, and the beautiful, dynamic rotation will be converted into the static, disordered geometry of a universe dominated by entropy. The ultimate fate of all motion in the universe is tied to the second law of thermodynamics. Entropy must increase. The spin, which is a form of highly organized, low-entropy motion, is constantly being converted into disorganized, high-entropy heat. In the far, far future, the universe will be cold, dark, and mostly empty, dominated by black holes and the remnants of stars. Even the black holes, the ultimate spinners, will eventually evaporate through Hawking radiation, and their angular momentum will be lost to the void. This evaporation is an incredibly slow process, taking more than 10 to the 100th power years for a stellar mass black hole. The universal spin, which began with a tiny necessary flaw in the Big Bang, will end with the final, slow, and inexorable triumph of entropy. The cosmic dance will slow, the music will fade, and the universe will finally approach the state of perfect stillness and maximum disorder. The universe will have conserved its total angular momentum, but that momentum will be so dispersed and disorganized that it will no longer manifest as the beautiful, spinning structures we see today. The age of spin will be over, replaced by the final silence of the heat, death of the universe. We've now traced the story of spin from the quantum foam of the Big Bang to the final silence of the heat death. But the universal spin is not just a physical phenomenon. It is a profound philosophical statement about the nature of our reality, and it holds the key to some of the most speculative and mind-bending theories in physics. Let us return to the deepest connection between spin and the fabric of reality, the concept of torsion. As we discussed in some extensions of general relativity, such as the Einstein-Cartan theory, space-time is not only curved by mass and energy, gravity, but also twisted by the intrinsic spin of matter, torsion. In this theory, the quantum spin of every fermion, every electron, every quark, is not just an abstract number. It is the source of a tiny localized twist in the geometry of space-time. Imagine the fabric of space-time as a vast, continuous sheet. Mass causes it to dimple, curvature/gravity, but spin causes it to twist, torsion. The collective aligned spin of matter in the universe would create a subtle, universal twisting of space-time. This is a profound idea because it means that the spin of matter is not just in space-time, but an active participant in creating the geometry of space-time. The spin statistics theorem, which dictates the behavior of all matter, is thus directly linked to the structure of the cosmos. If this theory is correct, the answer to why does everything spin is that the spin itself is a fundamental geometrical property of the universe, as essential as mass and energy. The universal spin, in its role as the ultimate manipulator of space-time, offers a tantalizing, albeit theoretical, pathway to faster-than-light travel. The concept of a warp drive, most famously articulated by physicist Miguel Alcubierre, is rooted in the mathematical possibility of manipulating space-time itself. The Alcubierre drive requires the creation of a local warp bubble that contracts space in front of a spacecraft and expands it behind. allowing the craft to travel vast distances without violating the speed of light locally. The challenge is that this requires the generation of immense amounts of negative energy density to sustain the warp bubble. Where does spin come in? As we explored with the Penrose process, the rotational energy of a spinning black hole is the only known, non-trivial way to extract energy from space-time itself. The Penrose process, which taps into the black hole's spin, is essentially a controlled manipulation of the Kerr metrics' twisted spacetime. Some speculative theories suggest that a controlled, localized torsion, a twist in spacetime, linked to the spin of matter, could be a key ingredient in manipulating the vacuum energy required for a warp drive. If the universe's spin is a geometrical property, then perhaps advanced civilizations could learn to mimic and manipulate that property, creating a localized, controlled spin in spacetime to achieve interstellar travel. The ultimate mastery of spin may be the key to the stars. Finally, the universal spin offers a powerful philosophical lens through which to view our place in the cosmos. The universe is not a static painting. It is a dynamic, rotating sculpture. The spin is the ultimate reminder that motion is the default state of existence. The conservation of angular momentum is the universe's cosmic memory. It ensures that the tiny, random twist of the Big Bang is preserved and amplified into the colossal spiral of a galaxy. Nothing is lost, it is only transformed. Every rotation, every orbit is a physical echo of the universe's beginning. The universal spin is a testament to the fact that the universe is a gyroscope. A gyroscope is a spinning wheel whose angular momentum makes it resistant to changes in its orientation. The spin of the Earth stabilizes its axis, giving us stable seasons. The spin of a galaxy stabilizes its disk, preventing it from collapsing into a chaotic blob. The spin is the force that brings stability and order out of the initial chaos of the Big Bang. The fact that we exist, that we are not torn apart by the chaos of the cosmos, is a direct result of the universal spin. It is the force that organizes, protects, and sustains. It is the silent, invisible rhythm that governs all things, from the quantum to the cosmic. The universal spin is the ultimate, enduring truth of a universe that is forever in motion. The universal great sculptor of cosmic structure, the force that transforms featureless clouds of gas into the breathtaking variety of stars, planets, and galaxies we see today. To truly understand why everything spins, we must delve into the chaotic, yet ultimately ordered, process of structure formation and the persistent challenges it presents to our models. We know that stars are born from vast, cold molecular clouds. These clouds are not static. They are highly turbulent, a swirling, chaotic sea of gas and dust. This turbulence is the key to both the collapse and the rotation of the star. The initial turbulence within the cloud contains a complex mixture of linear and rotational motion, known as vorticity. As gravity begins to pull a denser region of the cloud inward, this initial, chaotic vorticity is captured. The conservation of angular momentum then dictates the subsequent fate of the collapsing core. The problem, however, is that a typical molecular cloud core contains far too much angular momentum to collapse directly into a single star. If the angular momentum were perfectly conserved, the centrifugal force would stop the collapse long before the star could form. This is known as the angular momentum paradox in star formation. Nature's solution to this paradox is multifaceted, and it is the reason why single stars are the exception, not the rule. the cloud fragments into smaller clumps. Each fragment carries only a fraction of the total angular momentum, allowing it to collapse further. This is why most stars are born in binary or multiple star systems. The initial angular momentum is converted into the orbital angular momentum of the companion stars. The magnetic field lines embedded in the gas act like stiff rubber bands. As the core begins to spin, the magnetic field lines drag the surrounding, slower-moving material with them, transferring angular momentum away from the core. This magnetic braking is crucial for allowing the star to collapse to its final size. The remaining angular momentum is channeled into the formation of the protoplanetary disk. The disk acts as a massive angular momentum sink. Material spirals inward toward the star, losing angular momentum through viscous forces and magnetic fields, while the vast majority of the angular momentum is carried outward by the disk itself. This is a continuous, dynamic process of angular momentum redistribution. Once the planets form within this spinning disk, their own rotation is a complex inheritance. While the planet's orbit and its rotation, spin, are generally aligned with the original disk, the specifics of the planetary spin are a record of the system's violent history. The most common explanation for the non-alignment of planetary spins is giant impacts. The Earth's own 23.5-degree axial tilt, which gives us our seasons, is widely believed to be the result of a colossal impact with a Mars-sized body, Theia, early in its history, an impact that also created the Moon. This single event fundamentally altered Earth's spin, setting the clock for our climate and life. Similarly, the extreme tilt of Uranus, which spins on its side, and the retrograde, backward spin of Venus are thought to be the result of one or more massive chaotic collisions. These events did not destroy the angular momentum. They merely reoriented it. The total angular momentum of the solar system remains conserved, but the spin of individual bodies is a dynamic, evolving property, constantly being reshaped by gravitational and collisional forces. The discovery of the rotation of the cosmic filaments, the largest spinning structures in the universe, has opened a new frontier in the study of spin. These filaments, composed of galaxies and intergalactic gas, are rotating at speeds of up to 100 kilometers per second, and their rotation can extend for hundreds of millions of light years. This colossal spin is a direct observable confirmation of the tidal torque theory on the largest scale. The initial, tiny twists in the early universe were amplified not just into galaxies, but into the very scaffolding that connects them. The rotation of the filaments is a crucial piece of the puzzle, as it shows how the angular momentum is transferred from the largest scales of the universe down to the individual dark matter halos, and finally to the spiral galaxies within them. The universal spin is a continuous, interconnected process. The turbulence in a molecular cloud, the tilt of a planet, the spiral of a galaxy, and the spin of the cosmic web are all different manifestations of the same fundamental law, the conservation and redistribution of angular momentum. It is a story of chaos giving rise to order, where motion is the architect of everything we see. The universal spin is not merely a mechanical process, it is a fundamental pillar of our reality, inextricably linked to the concepts of time and life itself. This connection is so profound that it touches upon the very definition of existence and the possibility of life beyond Earth. The relationship between spin and time is more than just a matter of measurement. it is a matter of definition. In physics, time is not an absolute entity, it is the measure of change. Without motion, there is no change, and without change, there is no time. Every rotation in the cosmos, from the electron's spin to the Earth's rotation, provides a stable, repeatable cycle that allows us to define and measure time. The regularity of these cycles is a direct consequence of the conservation of angular momentum. The stability of the Earth's rotation, for instance, is what gave rise to our concept of the day. The incredible precision of pulsars allows them to act as the most accurate natural clocks in the universe, their spin so stable that they are used to test the limits of general relativity. Einstein's theories revealed that time is not absolute. The faster an object moves, the slower time flows for it relative to a stationary observer. This time, dilation is a direct consequence of motion. A rapidly spinning black hole, through the frame-dragging effect, literally twists the time dimension along with the space dimension. The time experienced by an observer near the black hole is drastically different from the time experienced by a distant observer. The spin is a local, physical force that actively warps the flow of time. The direction of time, the fact that it flows forward, is governed by the second law of thermodynamics. Entropy must increase. Spin, which is a form of highly organized, low-entropy motion, is constantly being converted into disorganized, high-entropy heat through processes like tidal friction and viscous dissipation. This constant, irreversible degradation of rotational energy is one of the primary drivers of the universe's march toward maximum disorder, giving time its forward-pointing arrow. The spin is the engine that drives the cosmic clock, and its gradual winding down defines the ultimate fate of time itself. The universal spin is a fundamental filter in the search for life beyond Earth, a key component of the anthropic principle, the idea that the universe's properties must be consistent with the existence of human life. The fact that the universe is not perfectly still is a necessary condition for our existence. The single most critical role of spin for life is the generation of a protective magnetic field. The geodynamo, powered by the Earth's rotation and internal heat, creates the magnetosphere. This shield is essential for deflecting the lethal solar wind and cosmic rays. Without a sufficient spin rate, a planet cannot maintain this shield. The vast majority of exoplanets, especially those orbiting small, dim, M-dwarf stars, are likely tidally locked, meaning one side perpetually faces the star. This slow or non-existent spin relative to their star makes them highly vulnerable to radiation, drastically reducing their habitability. Simply put, the spin is the first great test for a life-supporting world. Earth's rotation creates the cycle of day and night, which is crucial for regulating global temperatures. A tidally locked planet would have one side boiling and the other freezing, making it extremely difficult for complex life to evolve. Furthermore, the Earth's rotation drives the Coriolis effect, which is responsible for the formation of organized weather patterns, ocean currents, and the distribution of heat around the globe. This dynamic, stable climate is a direct product of our planet's spin. The rotation of the Milky Way itself is also crucial. Our solar system is positioned in the galactic habitable zone, a ring far enough from the chaotic, radiation-filled center of the galaxy, but close enough to have access to the heavy elements necessary for life. Our stable, near-circular orbit around the galactic center is a consequence of the galaxy's organized spin. If our orbit were highly elliptical, we would pass too close to the dangerous inner regions, sterilizing the planet. The universal spin is the cosmic gatekeeper. It sets the rules of the game, dictating where and how life can emerge and survive. The rotation of the cosmos is the ultimate reminder that the universe is a finely tuned, dynamic symphony where motion is life and the dance never ends. We have explored the spin of matter, from the quantum particle to the colossal black hole, but the universal spin extends its influence to the very messenger of the cosmos, light. The interaction between spin and light is a profound connection that allows us to decode the magnetic fields and the rotational history of the universe. Light is composed of photons, which are massless particles that travel at the speed of light. Like all particles, the photon has an intrinsic spin, which is an integer value of 1. This spin is directly related to the light's polarization. Polarization refers to the orientation of the electric and magnetic field, oscillations of a light wave. Since the photon has a spin of 1, it can only be polarized in 2 ways relative to its direction of motion. Left circular polarization. The electric field vector rotates counterclockwise. Right circular polarization. The electric field vector rotates clockwise. Each photon of circularly polarized light carries a tiny fundamental unit of angular momentum. This is the spin of the light itself. The spin of light is not just a theoretical curiosity, it is a practical tool used by astronomers to map the cosmos. The most powerful way light spin reveals cosmic secrets is through Faraday rotation. This phenomenon occurs when linearly polarized light passes through a magnetic field in the presence of free electrons, a plasma. The magnetic field causes the plane of polarization of the light to rotate. The amount of rotation is directly proportional to the strength of the magnetic field and the density of the plasma. By measuring the degree of rotation of the light from distant radio sources, astronomers can map the magnetic fields of the Milky Way and other galaxies. This is a direct, observable link between the spin of the photon and the magnetic field generated by the spin of matter. The magnetic field, created by the differential rotation of the galaxy, the galactic dynamo, leaves its fingerprint on the spin of the light passing through it. Faraday rotation is the ultimate cosmic decoder, allowing us to see the invisible magnetic scaffolding that is shaped by the universal spin. Beyond the intrinsic spin of the photon, light can also possess orbital angular momentum, OAM. This occurs when the light beam itself is twisted into a helix or a vortex shape. These twisted light beams are not just theoretical. They can be created in a lab and are a subject of intense research. A twisted light beam carries a much larger amount of orbital angular momentum than the intrinsic spin of its photons. This OAM is a new degree of freedom for light, and scientists are exploring its use in everything from high-capacity data transmission to probing the rotational motion of microscopic objects. The study of OAM in light is a direct parallel to the study of orbital angular momentum in the cosmos. Just as the orbital motion of planets is distinct from their axial spin, the OAM of a light beam is distinct from the intrinsic spin of its photons. It is a reminder that the principles of angular momentum are universal, applying equally to the motion of matter and the propagation of energy. The universal spin, therefore, is carried by the very light that allows us to see the cosmos. It is the spin of the photon that is twisted by the magnetic fields of the galaxy. allowing us to map the invisible forces that govern the cosmic dance. The spin of light is the language of the cosmos, and through it, we can read the rotational history of the universe. We have completed our journey through the universal spin, a journey that has taken us from the quantum foam of the Big Bang to the final silence of the heat death, from the spin of an electron to the twist of space-time itself. The answer to the question, why does everything spin, is not a single, simple sentence. It is a symphony of physics, a testament to the elegance and power of a single, unbreakable law, the conservation of angular momentum. The universal spin is a testament to the fact that nothing is ever truly lost. The tiny, random, initial angular momentum of the Big Bang was not dissipated. It was conserved, amplified, and transformed into the spiraling arms of a galaxy, the protective shield of a planet, and the quantum integrity of matter. The universe is a closed system, and its total angular momentum is constant. This means that every time you see a spinning galaxy, every time you feel the rhythm of day and night, you are witnessing the redistribution of an ancient, finite resource. The spin is the enduring link between the first moments of creation and the present moment of observation. The spin is the cosmic dance of creation. It is the constant, relentless motion that transforms raw energy into structure, chaos into order, and possibility into reality. Look at your hand one last time. You are not still. You are a passenger on a spinning planet, orbiting a spinning star within a spinning galaxy. You are a complex arrangement of spinning atoms protected by a spinning magnetic field. You are, in every sense, a child of the universal spin. The rotation of the cosmos is the ultimate reminder that the universe is not a machine that works perfectly, but a dynamic, evolving symphony where motion is life and the dance never ends. If this journey into the heart of cosmic motion has captivated you, if it has changed the way you look at the world, then the story is not over. The universe is still turning, and there are countless more depths to explore. Join us on the next chapter of Cosmo Depth by hitting that subscribe button and turning on notifications. Share this video with anyone who's ever looked up at the night sky and wondered why. Thank you for traveling with us to the edge of motion and the heart of the cosmos. Until next time, keep looking up and keep spinning.